we've already looked at finding the area between two curves. Now we're going to go ahead and take it to the next level. We're going to be looking at solids of revolution. And so, for example, we could be given a curve, let's say y equals x squared plus 4, and our instruction is to revolve this region, or revolve the curve about the x-axis from 0 to 3. So when we're talking about revolving a region about the x-axis, it's helpful if you can visualize, and it can be hard to visualize at first. So here's our curve, y equals x squared plus 4. It has a y-intercept of 4, and it's a parabola. When it says revolve, we're going to actually go ahead and spin that around the x-axis. So we're going to imagine taking a little piece, picking it up, revolving it around the x-axis, and then that region would go behind the paper and then come back up. So this revolution would make one little cylinder. And then we could do another little piece where this piece would be shorter because it's under a shorter part of the curve. It would come up, get revolved about the x-axis. And then same thing, add up all those pieces, that would give us an approximation for the volume when it's revolved about the axis. Using calculus, however, we can exactly find, as this distance here goes to 0 and we get infinitely many of those cylinders, we can perfectly find the volume of the area, or the volume of the region revolved about the x-axis. If all of these rectangles get infinitely thin and there are infinitely many of them, it will perfectly touch the curve, giving us a perfect volume. So what does that look like? Since we are going to be using cylinders, because that's how we are going to add up the volume of all the different cylinders, we need to know that the volume of a cylinder is given by volume equals pi r squared h. In this case, we're going to be taking the volume of pi, that's a constant, so we can just write it there, but we're going to take the integral, because we're going to be adding up all of the rectangles, or all of the cylinders together. So we're going to use that integral. It will sum them up as they get infinitely small. The radius squared h, and we're going to integrate that from 0 to 3, because that's the region the problem told us to find. So now we just need to figure out what is r and what is h. So going back to the visual, r is going to be the distance from the x-axis to the curve. So that will give you the radius. As it comes up and down, it'll be the same in this direction and this direction. That distance is given by the function, because the radius is going to be different for each piece. However, we can find what the radius is based on the function. So our radius is some function squared. Our height is going to be, if you look in this direction, the height is given by this distance right here. But this distance is going to be getting infinitely thin, smaller and smaller and smaller and smaller and smaller. As that happens, we're going to call that dx. It's the change in x. So it's going to be getting smaller and smaller, and we still have our pi out here. Since our function was y equals x squared plus 4, that's what we're going to plug in for the radius function. So x squared plus 4 squared dx. Once I have that set up, we can go ahead and evaluate just like we would solve any integral. So I'm going to go ahead and FOIL that out. X to the 4th plus 4x, or plus 8, excuse me, x squared plus 16 dx. Still integrating from 0 to 3. Then I can go ahead and add 1 to the power, divide by the new power. Add 1 to the new power, divide by the new power. evaluate from 0 to 3. And then go ahead and plug in 3, and then subtract off 0. So we get 3 to the 5th over 5, plus 8 times 3 to the 3rd over 3, plus 16 times 3. And when we plug in 0, each of these terms will go away, so we're only going to be subtracting off 0, which won't change it. This turns into 243 over 5, plus 216 over 3, plus 48. And when you simplify that all down, find a common denominator of 15. That comes out to be 168.6, changed it to decimals, times pi. Or if you plug in 3.14 for pi, comes out to approximately 529.4. Often, however, you'll see the final answers left in terms of pi. So that's the volume if you rotate x squared plus 4 about the x-axis from 0 to 3. We can also go ahead and do this about a line that is not the x-axis. So we could find the volume of the solid created by revolving y equals 2 minus x squared about the line y equals 1. So let's take a moment to visualize what that would look like. It's always helpful if you can draw a picture first. And we have y equals 2 minus x squared. So it's going to intersect the y-axis at 2, and it's a negative x squared, so it's going to be a parabola opening downwards. And then the line y equals 1. So we're trying to revolve this region here about this line. So to do that, after we revolve it, I always like to think what it will look like. I'm going to pick that region up, paste it down, and then it would go back through the back. So it's going to look kind of like that. Make a little football. So we're still going to follow the volume equation of V equals pi r squared h. The only difference is that we're going to need to find our limits of integration this time, and our r is going to be a little bit different because it doesn't go all the way to the x-axis. So let's go ahead and get started. Volume equals pi integral, and our limits of integration are going to be where these two functions intersect, right here and right here. So you can find them by setting them equal to each other. So 2 minus x squared equals 1. Subtract 2 from both sides. Negative x squared equals negative 1. X squared equals 1. X equals plus or minus 1. So that tells us they intersect when x is plus or minus 1. So that's where we're going to integrate from. And our r function is going to be given by this distance here. So it's going to be the function minus 1. The difference between the function and 1, not the x-axis. So our function is going to be 2 minus x squared, the top curve, minus the bottom curve. All of that squared, because all of that is the radius. And then dx, again, is the height of each cylinder. That's going to get infinitely thin. Once I have this, I can simplify and evaluate. So it'll turn to negative x squared plus 1 squared square that out, I get x to the 4th minus 2x squared plus 1 and then add 1 to the new power, divide by the new power. And then I can go ahead and plug in. And I get pi times 2/5 minus 4/3 plus 2. Find a common denominator, add those together. It comes out to be 16/15 pi. And again, we'll leave that in terms of pi because that is the exact volume if you rotate that curve about the line y equals 1. Last, we can find the volume by revolving around the y-axis. Okay, so we're going to find the volume when revolving this curve about the y-axis from 0 to 1. Again, always start with a visual. This curve touches at 0, 0 and 1, 1. And we're going to revolve it about the y-axis from 0 to 1 in the y direction. So we're going to revolve this region here. So always like to visualize picking that region up. It goes over and around, so it will be reflected over here, and then it will go back through. So it will be making a shape kind of like a solid funnel. Okay, and that's what we're finding the volume of. If you can visualize it, that's great. That's very helpful. Still going to start with our volume of a cylinder, because that's what we're adding up, infinitely thin cylinders. So the pi is a constant. We're going to integrate from 0 to 1 in the y direction. And when we evaluate this, our radius is going to be given by this distance here. So it's the curve minus 0. However, we need to get that in terms of y, because this distance here, the height, is going to be dy. So to do that, we can start with y equals x to the 2/3. Take the 3/2 power of each side. And x equals y to the 3/2. So we're going to plug in y to the 3/2. That region is our radius, so that will be squared. And h is dy this time, because again, our cylinders are stacked in the y direction, change in y. So I'm going to go ahead and square those. That will give me y to the 3rd. And now I can go ahead and integrate, add 1 to the power, divide by the new power, evaluate from 0 to 1, which when I plug in 1, I will get 1/4. Plug in 0, you'll get 0. So the volume will be exactly 1/4 pi when we revolve that region about the y-axis. So in summary, it matters which direction you are going. If you have a horizontal axis of symmetry or if you have a vertical axis of symmetry. Axis of revolution. If you have a horizontal axis of revolution, you're going to be doing volume equals pi integral from a to b of whatever function gives you the radius squared with respect to x. If you have a vertical axis of revolution, you are going to have volume equals pi, integrate from c to d, make sure those are in the y direction. Whatever function gives you the radius in terms of y squared, and the height will be given by dy. With that, you should be good to go.